Welcome to this lecture. Before we proceed, let's quickly recall what we have been doing in this week. So we have looked at certain class of functions defined on the sample space and we considered the measurability properties. We defined it as the functions for which the pre-images of all measurable sets from the range side, those pre-images should lie in the domain side sigma field. And in particular, we are interested in the functions which take values in the space of real numbers or extended real numbers or in higher dimensional Euclidean spaces. So there we are putting the appropriate Borel sigma fields on the range side and looking at all Borel sets on the range side, looking at their pre-images. If the pre-images fall inside the domain side sigma field, then we are calling it as Borel measurable functions. So we have so far discussed three types of examples of such functions. First were constant functions, second indicator functions, and third continuous functions. So continuous functions we considered on the real line and also on higher dimensional Euclidean spaces, and we considered the ranges as either the real line or some RT. So with such appropriate assumptions, we have mentioned that such functions are also Borel measurable. So we have such types of examples at hand. So with this, we are now going to proceed and look at certain nice properties of these functions, and as we shall see that these properties also allow us to construct more examples from the existing examples. Okay. So in this lecture we are going to discuss algebraic properties of these functions. So basically we are going to look at algebraic operations on these functions like addition and subtraction. So let's move ahead with the slides. So in the last two lectures we have discussed this concept of Borel measurable functions. In this lecture we are going to focus on these algebraic properties of these functions. And as mentioned earlier, we are going to see that these properties are going to help us construct more examples. So the first property that we are going to look at is described in this proposition. So what we are saying is that I am given two measurable functions. First one goes from omega 1 to omega 2, and then the second function goes from omega 2 to omega 3. So if you are just given these two functions f and g, so you can talk about the composition of the functions g compose f, whose domain is omega 1, and the composition should land up in omega 3, right? So f goes from omega 1 to omega 2 and then g takes over, it takes from omega to omega 3. So therefore the composition is fine and you can talk about the composition from omega 1 to omega 3. See here, of course you require that the range of f should be contained in domain of g. And here it's perfectly fine because the range of f will be some subset of omega 2 and omega 2 is the domain of g. G composition f is well defined, so that is not a problem. Now we are going to claim that this composition will be measurable provided f and g were given to be measurable. So now when you are looking at f, you will have appropriate sigma fields on the domain side and the range side, and you will require the appropriate measurability assumptions on f. Similarly for g, you will put the appropriate sigma fields on the domain side and the range side. So it's important that you keep the sigma field on omega 2 to be the same. So you keep the same sigma fields. So then you also assume that g is also measurable. So given that f and g are measurable, we claim that g composition with f is also measurable. So how do you go about proving this? So again, let's go back to the definition. So you want to show that for arbitrary sets on the range of g composition f, so the range is omega 3 and there the sigma field is script f3. So you will take arbitrary sets from there and you would like to look at the pre-image under the composition map. If the pre-images fall inside the domain side sigma field, which is script f1, then you will claim that g composition f is measurable. So how do you check this? So first observe that if you look at the measurability of g, you will immediately claim that for any arbitrary measurable set in f3, which is in omega 3, you look at the pre-image under G, so that will fall inside the domain side sigma field of G. So what is the domain of G? That is omega 2, and that domain side sigma field is script f2. So therefore the pre-image of A under the function G, that will land up in script f2. This is by the measurability of G. But then you use the measurability of f and look at the pre-image of the set G inverse of A under the function f. So G inverse of A is in script f2, and use the measurability of f. So f goes from omega 1 to omega 2. So now you will take any set from the range side which is in script f2. So you can look at this set G inverse of A. So that set, if you look at the pre-image under f, so that should land up in script f1 as per the measurability of f. But this is a easy statement to check that G composition f, that function, that composition function, if you look at the pre-image of the set A under this function, it can be written as this pre-image, meaning it's the pre-image of G inverse of A under the function f. Okay, so if you show this equality, you will immediately claim using the measurability of G and f that the pre-image of A under G composition f is in f1. And therefore, since you have proved it for any arbitrary set A in f3, script f3, therefore you can claim that G composition f is measurable. Okay, so this is a very important property, and you are going to see the usage of this right now. Okay, so now what is this? So we are going to apply this composition operation now. So what is the statement? So I am starting off with now one measurable space omega script f, and look at some arbitrary function defined on omega. So taking values in some Euclidean space Rd. Okay, so now you can write the component functions as f1, f2, fd. So what are these? These are all the functions which take component wise values. So how are they defined? So you take f of some sample point small omega. So f of small omega will be a vector in Rd, and the first component of that will be given by the function f1. Second component will be given by the function f2. So all of these functions fi, f1, f2, fd, these functions fi are functions from omega to r. So these are taking values in the real line. So you can identify these component functions as long as you are given the function f. Now here is the statement. So take f to be Borel measurable. That means you are looking at appropriate sigma fields on the domain side, scripted f, and appropriate sigma fields on the range side. So that will be the Borel sigma fields. Then with respect to these sigma fields, you talk about the measurability of the function f. Now if this is Borel measurable, the statement says that the component functions fi are also Borel measurable. Now remember that these component functions fi are from omega to r. So therefore you are going to use the Borel sigma field of the real line on the range side. And you are claiming that if f is measurable, then fi's are also measurable. But this statement says something more, that if you know that the component functions fi's are Borel measurable, so you have d many component functions which are Borel measurables from omega to r, then the original function f is also Borel measurable. So this is an if and only if statement. So how do you prove this? So the proof goes by checking the measurability conditions on generating sets on the range side. So this was mentioned earlier in note 13, that we can check this just the measurability conditions or the pre-image of sets coming from the generating class on the range side. So what to do? So start with these projection maps, coordinate projection maps that were mentioned earlier. So these were also continuous functions, and these turned out to be Borel measurable by the appropriate condition that we just mentioned, by looking at the pre-images of the generating sets. Now we are going to use those two things together. So one is about this pre-image of generating sets. So that's one thing that we are going to use. The second thing that we are going to use are these coordinate projection maps pi I. So how do you proceed? So start with Borel measurability of the function f, which is from omega taking values in Rd. So then what you can look at are these component functions can be obtained as a composition of the projection maps with the actual function f. So this is pi I compose f. So you can easily check this. So take a sample point omega in the domain. So then if you look at pi I composition with f evaluated at that sample point small omega, you will exactly get back the ith component function. Okay, so that's this relation here. So now as soon as you have the Borel measurability of f, put it together with the Borel measurability of the functions pi I, and then by the composition operation that was discussed in proposition 2 above, you immediately claim that the component functions fi are also Borel measurable. So you see the proof is very simple as long as you know all these facts. Okay, so now for the converse, we are going to use this thing about the pre-image of generating sets. So now we are assuming that all the coordinate functions fi's are Borel measurable. So they are from omega to r. So you are using the Borel measurability there with the real line, the Borel sigma field on the real line on the range side. But then you want to claim the Borel measurability of the function small f, which is taking values in Rd. So you will be using the Borel sigma field of Rd. So to check the Borel measurability of the function f, you need to use the generating sets of Borel sigma field on Rd, which is the range. So then you use that. And what are the generating sets there? So recall from our discussions in week 1 that for this you have to use this product of this type of left open right closed intervals. So you will choose these numbers ai bi, ai strictly less than bi, and look at these intervals ai bi, take the product of them, d-fold product. So these are all the generating sets on the Rd. So the Borel sigma field of Rd, right? So therefore if you look at the pre-image of these sets and if you just verify the appropriate condition for these sets, then you are done. But then it's easy to check that the pre-image under f, that can be written as this condition. So what are these? You are saying that these points that are in this pre-image, so for these points the ith component lies in ai to bi. So that's what the left hand side means, right? So if you put a sample point on the left hand side, then f of omega lies in this product. So therefore individually component wise the ith coordinate lies in ai to bi, that left open right closed interval, correct? And that's what exactly is stated on the right hand side. So check this, and therefore what you are able to write is that the left hand side is equal to the right hand side, where on the right hand side you have the pre-images involving the component functions. So now in these component functions, if you assume the measurability as given in the hypothesis, then this pre-images lies in the domain side sigma field, which is scripted f, and therefore the finite intersection is available there, and therefore the right hand side is falling inside the domain side sigma field. Therefore using the Borel measurability of the component functions fi's, you get the measurability of the function small f. Okay, this completes the proof. So now what is this identification once more? So using these composition operations that we discussed, we have been able to show that if you want to talk about Rd valued measurable functions, it's good enough that you talk about the measurability, the real valued measurability of the component functions, and vice versa. So that is the identification, that as long as you have d many component functions which are measurable, put them together, you will get a Rd valued measurable functions. On the other hand, given a Rd valued measurable functions, the component functions immediately turn out to be Borel measurable. Okay, so with that result at hand, we are now going to proceed towards certain interesting observations. But first, in exercise 4, we mentioned that all these results that are discussed for the real valued functions or Rd valued functions can be extended with extended real line as the range side. Okay, but this we are not going to use too much. So on the range side, where we have to use r bar d when you are looking at the d-dimensional versions, but you can still use usual ideas to talk about the Borel sigma fields on r bar d. So we have skipped that in the discussions in week 1, but you can still talk about the Borel sigma fields on r bar d, the d-fold product of the extended real lines, by usual method, by looking at products of d-fold products of the generating sets left open right closed intervals on the extended real line. So So if you look at such sets, it will generate the appropriate sigma field, and you can actually prove the analogous version of this identification of r bar d valued measurable functions with the measurability of the component function. So you can prove this. So this is a optional exercise given to you. So in all of these results that we are going to state, many of these results can be stated either for real valued functions or extended real valued functions, and according to our convenience we are going to look at any one of these versions. Okay, so now we are going to go forward and discuss the main result of this lecture. Okay, so what is this? So look at functions f comma g defined on the same measurable space and taking values in the real line. So these are all given to be Borel measurable functions. Then what we are going to say that look at other functions like this. So what are these? So look at f plus g. So how is f plus g defined? So look at a sample point small omega. F plus g, that function is simply taking the value f of omega plus g omega. So just evaluate the original functions f and g at the sample point, add them up, you will get the actual function f plus g. Similarly, f minus g, that function is defined as f of omega minus g of omega. So likewise, you can go ahead and talk about all the other functions like f times g, so product of f and g, modulus of f, minimum of f and g, maximum of f and g, such functions. In particular, recall that constant functions are always measurable. In particular, if you take g to be identically 0 function, then you can look at maximum of f and 0 and maximum of minus f and 0, such functions. Okay, so here just a quick note that minus 1 is also a constant function. Minus 1 is a constant function and it's also Borel measurable. So now we can talk about the product f with the constant function minus 1. So that will give you the function minus f. Another way to look at this function minus f is to look at the subtraction from 0. So 0 minus the function f will give you minus f. So since both the functions 0, the constant function 0 and f are measurable, the function minus f is also measurable. What we are doing, we are looking at this maximum of f and 0 or maximum of minus f and 0, and we are going to write as f plus and f minus, these two functions. We will see the usage of these functions in a minute. Okay, but what we are saying is that all these functions that we are talking about, they also be Borel measurable. So provided f and g are Borel measurable, you will immediately get the Borel measurability of f plus g and so on. So now let's quickly mention the usefulness of f plus and f minus. So what are these functions? So when the function f is taking non-negative values, then f of omega is non-negative, so the maximum of f of omega and 0 will turn out to be f of omega. So f plus will be taking the value f of omega for those points where f is already non-negative. But if f is taking negative value at some point, then f of omega is negative, so the maximum is 0 here. So therefore f plus will be taking the value 0. So therefore you are looking at the graph of the function small. As long as it is above the value 0, as long as it is above the x-axis in some sense, then what you are doing is that you are looking at only that part. As long as it goes below the value 0, you ignore those values and put the function, constant function 0 there. Okay, so that's what the function f plus is. It's called as the positive part of the function small f. Okay, you just look at the points where the function f is taking positive values, and that's where you concentrate your attention and obtain this function f plus. On all the points where f is taking negative values, you assign the value 0. Similarly, f minus is called the negative part of f. It's the amplitude or the modulus value of how far below f is from 0. So as long as f is taking negative values, let's say minus 2, if you compute the value, it will turn out to be 2. So basically it is giving the modulus of the distance from the 0. Okay, so f minus is saying that how far below the function f is from 0. So that's the negative part of f. Okay, alright. So let's go ahead and prove this theorem that provided f and g are measurable functions, Borel measurable functions, then all these algebraic operations will give you measurable functions. So with this at hand, as long as you have some examples, explicit examples, you can use these algebraic operations to construct more examples. So the proof is pretty simple and it has the same structure for all these functions. So we discussed the proof for f plus g. For all the other functions, you can try to work them out. So how do you prove the measurability of f plus g? So remember, f plus g is a function from omega to r. So again, you are using the domain side sigma field scripted f and the range side sigma field Borel sigma field or r. So how do you prove the measurability? Okay. So observe first that as long as f and g are Borel measurable, you can talk about this function f comma g. So this is a two-dimensional function taking values in R2. Okay. So for each point in omega, you look at f of omega comma g of omega. So that's a value in R2. Okay. And by the earlier proposition, as long as these component functions f and g are Borel measurable, this two-dimensional function taking values in R2 is also Borel measurable. So this is immediately where we are applying this proposition. But now note that you have this addition function on R2. We are calling the function as h. So h takes points xy in R2 and adds them up. So take the points x comma y and add up these values x and y. So that's your function. So that's a function from R2 to R. Observe that this is a continuous function. We had actually mentioned such functions from Rd to Rn, any two dimensions. So this will, if they are continuous, they will be Borel measurable. So in particular here, the function h from R2 to R is also measurable, Borel measurable, right? So therefore, what we are going to do is to use these two functions now. So the first function is made up of this R2 valued function f comma g, and the second function is this addition function h. Okay. So put them together. So look at the composition of h with the two-dimensional R2 valued function f comma g. So this composition, how does it go? So f comma g, that function goes from omega to R2 and h goes from R2 to R. So the composition goes from omega to R. But if you put the sample points there and compute this composition, what does it give you? It gives you the addition of f of omega plus g of omega for any sample point small omega, right? So given any sample point small omega, if you compute this composition at that sample point small omega, you will simply get f of small omega plus g of small omega, and that is nothing but the function f plus g. So therefore, f plus g being the composition of these two measurable functions becomes Borel measurable. So the proof is pretty simple as long as you use all these algebraic properties that you have already proved. For other functions like f minus g, you have to take the function h as going from x comma y to x minus y. Since that is continuous, it will be Borel measurable. Use the appropriate identification by the compositions and you will get the property. So once you have done the hard work, all these properties now follow pretty easily. Okay, alright, fine. So now one important fact is here that we have so far discussed addition, subtraction, multiplication and some related operations like taking modulus, maximum and minimum, right? But then one important operation is missing, that is the division. So you are interested in what happens if you divide a measurable function by another measurable function. But here you have to be careful. You cannot divide by any function which is taking value 0. So first of all, if you are dividing a real number by another real number, you have to be careful if the denominator is 0. So that is not defined, right? So this is a similar operation. When you are dividing a function by another function, you have to be careful that the denominator function is not becoming 0 at some point. So then it will not be defined. So therefore we are going to restrict our attention to r minus 0. So we will exclude the point 0 from the real line. So that will be considered for our range spaces. Okay, so here that's what we are going to consider the denominator on. Okay, so denominator will be taking values on r minus 0. It will not take the value 0. So then whenever you are going to talk about the range as r minus 0, then you have to talk about the appropriate sigma fields, and that was discussed earlier in week 1. R minus 0, remember this is a Borel subset. The singleton set 0 is a Borel subset, so their complement is also in the Borel sigma field, so it's a Borel subset. For Borel subsets we have defined the Borel sigma fields, so recall that construction there, and what we are going to talk about are divisions by functions by measurable functions. Okay, so continue with f as in real valued function, real valued measurable function on the measurable space omega script f. But now the function you are going to divide by, the function g, that you have to be careful with, and that's what we have just mentioned, that take the range space as r minus 0, so exclude 0 there. Okay, so here what happens, you have to put the appropriate sigma field here, Bodel sigma field on r minus 0. Then the claim f by g, that function, that is well defined, and that becomes measurable with respect to the appropriate sigma fields. Okay, so here what happens, the division is well defined. So this is a real valued function because f can take the value 0, right? So the division can produce the value 0 since the numerator is allowed to be 0, right? Okay, so how do you show this? So again, just to repeat, so this f by g is well defined as long as g takes non-zero values. But then observe that this function, the division operation that we have been discussing, can be written as this format, r cross r minus 0. So you take two real numbers x and y, but allow y to take values in r minus 0 only. So do not allow y to take the value 0. Then you can talk about x over y. So x over y will be some real number including 0. Okay, so this is the continuous function as long as you vary x and y in this space. Okay, so now the proof will follow similar to the earlier argument. Since this function, division function that we have been talking about here, this is continuous, it's also Bodel measurable, and hence if you compose with the function f comma g, the two-dimensional function taking values in r cross r minus 0, then the composition will give you a measurable function, Bodel measurable function. So therefore f by g, that's the resultant function, will turn out to be measurable with respect to the appropriate sigma fields. Okay, so the proof is pretty simple to work out. Alright, so a final exercise to finish off the lecture. So here what we have taken is that we have explicitly stated that the range of g is r minus 0. But suppose you look at this following variant of this hypothesis. So start with g to be measurable but with real values, but then you specify that the range is r minus 0. So what is the difference with the previous hypothesis? In the previous hypothesis you were only checking measurability for measurable sets coming from r minus 0, but now you are saying g is measurable with Bodel sigma field on r. So you have checked it for all Bodel subsets of r, not r minus 0, right? So with those measurable sets you have checked the pre-images, and that turned to be in the domain side sigma field, right? So now with this general condition, now you assume that the range of g is contained in r minus 0. Question is that whether g is now measurable with respect to the sigma field on r minus 0. Since g is taking values inside r minus 0, you can now consider this question that it's a mapping from omega to r minus 0, and you put the appropriate domain side sigma field scripted f, but the range side sigma field now you take it to be the Bodel sigma field on r minus 0. So given the fact that g was originally measurable with respect to the Bodel sigma field of r, with the additional fact that range of g is now r minus 0, can you say this? Okay, so try to work this out. Okay, so that's the exercise. So in this lecture we have looked at these algebraic properties including composition and all these usual arithmetic operations like addition, subtraction, multiplication and division. Okay, so these will be useful in constructing more examples, and we are going to discuss certain continuity or limiting properties of measurable functions in the next lecture. So we stop here.